Welcome to video number 4, I believe it is. This is the last video. We're going to do example number 3 and example number 5, and I'm going to leave example number 4 for you to look at and see if you can finish that off. And then if you have questions about how to do example 4, bring them to class and we can discuss it. But example number 3. What are we given? We're given the graph of f prime of x in the picture here. So two things. They're going to tell you what you're given here, and they're going to label what you're given here. Make sure to pay attention to what it is you're given. Find the intervals where f of x is concave up or down, and find any x values where f of x has a point of inflection. So I need to find the second derivative, but I'm given the first derivative graph. So I have to think about, what does that mean? Remember that when f of x is concave up, that means the second derivative is positive. But the second derivative is the slope of the first derivative, right? And I know that it's concave down when the second derivative of f is negative, and the second derivative is the slope of f prime, which is what we're given. So in other words, I know that the slopes are all positive, and maybe I'll use a different color here. I know that the slopes are positive in this section all the way until the very top. And I know my slopes are negative in this section all the way to the very bottom. So if the slopes of f prime are positive and negative, that means the second derivative values are positive and negative, and that is where f of x is concave up, and that's where f of x is concave down. So I'm going to make the two statements right here and say f of x is concave up. Let me make it a little bit bigger. Concave up on the interval for x's that are less than 1, because f double prime is greater than 0. And if you want to explain a little bit more, you can. You can say the slopes of f prime, but really this is all you need. And we can say f of x is the original function, which, by the way, I cannot see. The original function is concave down on x's that are greater than 1, because in that section, let's see, correct it here, because f double prime is less than 0, slopes of f prime are negative. Maybe we can write that. Over here, we'll say that they're positive. Again, the parenthetical part, that's up to you. I can put a period here, and that would suffice. But I guess I'm writing this to kind of help you, or help us realize what exactly we were looking at. We were looking at the slopes. They're all positive, and that would be the second derivative, because that would be the derivative of f prime, which is what I'm looking at. And then finally, is there a point of inflection? F of x has a point of inflection. Where does it occur? At x equals 1, because the second derivative changes signs at that point. You could say at x equals 1. I feel like if I already referenced the point over here, I don't need to write it again. I'm just going to say at that point. But you can most certainly say changes signs at x equals 1. That's why there's a point of inflection at x equals 1. And that's it. We successfully answered the question, and it wasn't that bad because they gave me the first derivative graph. However, you got to remember, what is it that you're looking for? What is it that you're given? What is it that I'm going to focus on so that you can answer the question correctly? We're going to do that again. We're going to do it with number 5. Another graph and another derivative. And again, they'll tell you what you're given. They'll label what you're given, just so that you know. You can't say, oh, I didn't know. Well, yeah, they told me that this is the graph of h prime. On what open intervals is h of x, which we cannot see, decreasing and concave up? Okay, so now I gotta put my thinking cap on here. I know that a function is increasing. Let me change the color here. I know that a function is increasing when h prime, the derivative of that function, is less than or equal to 0. And I know that a function is concave up when the second derivative of that function is greater than 0. Right? So that's what we've been doing the last couple of sections, is connecting the behavior of the graph with a calculus concept. So decreasing has to do with the first derivative being negative. Concave up has to do with the second derivative being positive. But we are given the graph of h prime. So then here, I guess we can say, when is the graph of h prime under the x-axis? And then here, I can say, when are the slopes of h prime positive? Because if I can figure out where these two things are happening at the same time, that's the answer that they want. Okay, so here we go. Where is the graph of h prime under the x-axis? Because that would be where h prime is negative, and that's where h is decreasing. So far, all of this qualifies. But now I go to the second part. The second part says, where is h double prime greater than 0? Where are the slopes of h prime positive? Well, that would be here and here. So therefore, that double shaded part satisfies both of those two conditions. That's the answer. They're asking for open intervals, so we can say h of x is decreasing and concave up on the interval between 2 and 5, or in the interval between 8 and 9. And I know that because the first derivative of h is less than or equal to 0, and, don't use or, and, because both things have to be true, the second derivative of h is greater than 0. And that's my answer. So maybe working with graphs is a little bit easier. You just have to make sure you're looking at the graph through the right lens so that you're answering the correct thing that they're asking you for. We'll practice this when you come in on next time, and we're going to use concavity to help us for two reasons. Number one, we're going to help ourselves find relative extrema using the second derivative, and we're going to be able to tell whether our tangent line approximations are overestimates or underestimates based on the concavity that we find for that given function. Other than that, this is the last video.